The paper proposes an identifiable cognitive diagnosis framework, ID-CDF, for personalized learner modeling, addressing the limitations of existing cognitive diagnosis models, CDMs, that suffer from non-identifiability and explainability overfitting problems. This framework is based on a novel response-proficiency-response paradigm inspired by encoder-decoder models. The diagnostic module of ID-CDF leverages inductive learning to eliminate randomness in optimization, guaranteeing identifiability and capturing the monotonicity between overall response data distribution and cognitive states to prevent explainability overfitting. A flexible predictive module is also proposed to ensure diagnosis preciseness. The implementation of ID-CDF, ID-CDM, is presented to illustrate its usability, and extensive experiments on 4 real-world datasets demonstrate its effectiveness in addressing the problems without loss of diagnosis preciseness. Cognitive diagnosis models, CDMs, face 2 significant challenges in personalized learner modeling: the non-identifiability problem and the explainability overfitting problem. The non-identifiability problem occurs when learners with the same response data distribution have different diagnostic results, making it difficult to distinguish between learners with different learning performances. This issue is prevalent in existing CDMs such as DINA and NCDM, as shown in Figure 2, where over 50% of the distance between diagnostic results of learners with the same response data is positive, indicating unidentifiable diagnostic results. The explainability overfitting problem arises when diagnostic results are highly explainable in observable response data for training but less explainable in unobservable response data for testing. This problem stems from the transductive learning process in the proficiency response paradigm, which is the cornerstone of many classical CDMs. The paper highlights that the monotonicity assumption between response scores and corresponding dimensions of learner traits is crucial for ensuring explainability, as actual cognitive states are latent and unobservable. Researchers have made efforts to enhance the explainability of CDMs through elaborately designed monotonic interaction functions and parameter constraints. A new paradigm for personalized learner modeling has been introduced to address these challenges. This new approach is based on a novel cognitive diagnosis model that utilizes a different optimization algorithm to improve the identifiability and explainability of diagnostic results. The proposed model uses a different optimization algorithm to enhance the stability and consistency of diagnostic results, leading to more accurate and reliable learner modeling. The proposed paper introduces an identifiable cognitive diagnosis framework, ID-CDF, to address the non-identifiability and explainability overfitting problem in cognitive diagnostic models, CDMs. This framework utilizes a novel response-proficiency-response (RPR) paradigm, designed to improve the usability of diagnostic results in web learning services. The paper begins by defining necessary mathematical notations and the CDBASED learner modeling task. It then discusses the concept of identifiability and explainability in CDBASED learner modeling, highlighting that distinct diagnostic results should lead to distinct response data distributions. The proposed ID-CDF consists of a diagnostic module that encodes response data into learner traits and question parameters, a predictive module for reconstructing response data, and an optimization module for ensuring the precision of diagnosis. The paper also presents an implementation of ID-CDF, called ID-CDM, to illustrate its usability. Experiments on 4 public real-world learner modeling datasets with different characteristics demonstrate the effectiveness of ID-CDF in terms of identifiability, explainability, and precision. The Identifiable Cognitive Diagnosis Framework, ID-CDF, tackles the non-identifiability and explainability overfitting issues in cognitive diagnosis models. This framework consists of 2 modules, diagnostic and predictive. The diagnostic module transforms response logs into response vectors for learners and questions, applying learner and question diagnostic functions to diagnose learner traits and question parameters. These functions are regularized by 2 conditions: identifiability, ensuring that diagnostic results are solely derived from observable response data, and monotonicity, requiring the probability of a learner correctly answering a question to increase with their relevant knowledge mastery level. This approach inductively obtains diagnostic results from response data, addressing the non-identifiability problem. The predictive module models the complex interaction between learners and questions, ensuring diagnosis precision. Built upon the response-proficiency-response paradigm, the ID-CDF framework provides a more accurate and interpretable learner diagnosis. By satisfying the identifiability and monotonicity conditions, the ID-CDF framework addresses the explainability overfitting issue, offering a more reliable and transparent cognitive diagnosis model. Personalized learner modeling using an inductive paradigm relies on the identifiability and explainability of its underlying mechanisms. A crucial component in achieving this is the diagnostic function f, omega, s, which satisfies the identifiability condition. This ensures that learner response data can be effectively vectorized as x's and x's, enabling the extraction of meaningful insights. To address the explainability overfitting problem, the monotonicity condition is also addressed. This guarantees that the model's predictions are transparent and interpretable. The predictive module, a key component of the ID-CDM framework, aims to reconstruct response scores from learner traits and question parameters. By leveraging neural networks, the diagnostic and predictive modules can capture cognitive states and question parameters from data, satisfying both identifiability and monotonicity conditions while ensuring diagnosis preciseness. The ID-CDM framework's strength lies in its ability to provide a comprehensive understanding of learner behavior, enabling the development of more effective personalized learning systems. By satisfying the identifiability and monotonicity conditions, the model ensures that its predictions are not only accurate but also transparent and interpretable, addressing the explainability overfitting problem. This approach has significant implications for the development of more effective and efficient personalized learning systems. The experimental setup of the research paper evaluates the performance of the proposed ID-CDM model against other CDMs by answering 4 key questions: identifiability, explainability, and precision of diagnostic results, as well as the statistical relationship between diagnosed learner traits and actual learner performance. 4 real-world datasets are utilized, including 2 online K-12 mathematical test datasets and 2 offline high school mathematical exam datasets. A novel experiment is proposed to evaluate the identifiability of various CDMs, addressing data sparsity through a data augmentation operation creating shadow learners. The identifiability score, IDS, is introduced as an indicator of identifiability, with higher values indicating better identifiability. An ablation study is also conducted to explore the impact of random initialization on existing CDMs and diagnostic modules, comparing results with constant initialization and without the diagnostic module. Experimental results are presented in Table 2, providing insights into comparative model performance. In the realm of personalized learner modeling, the quest for both identifiability and explainability is paramount. However, score prediction-based cognitive diagnostic models, CDMs, often fall short in generating diagnostic results that are identifiable due to the inherent randomness in optimization processes. This limitation hinders the ability to accurately diagnose learner knowledge gaps and tailor learning paths accordingly. To address this issue, the introduction of the Identifiable Cognitive Diagnostic Model, ID-CDM, offers a promising solution. By achieving a maximum identifiability score, ID-CDM provides a more precise and reliable means of diagnosing learner knowledge gaps, thus enabling educators to develop targeted interventions. Moreover, the evaluation of explainability in these models is crucial for understanding how they function and make predictions. 2 novel metrics, the degree of consistency, DOC, and the rate of explainability overfitting, RAO, have been proposed to quantify the explainability of CDMs. These metrics provide insights into the model's performance, allowing researchers to assess its reliability and potential biases. The experimental results, as depicted in Figure 5, demonstrate the ID-CDM's superior performance in both identifiability and explainability. The DOC and RAO metrics offer quantitative insights into the model's capabilities, highlighting its potential to revolutionize the field of personalized learning. The ID-CDM, along with its associated metrics, presents a significant advancement in cognitive diagnostic modeling. Its ability to provide identifiable and explainable results promises to enhance our understanding of learner knowledge gaps and improve the effectiveness of personalized learning strategies. The authors present the results of their proposed Identifiable Cognitive Diagnosis Framework, ID-CDF, on learner performance prediction and learner traits clustering. In Figure 6, ID-CDM outperforms baseline models in most cases, achieving higher accuracy, F1 score, and lower RMSE. This demonstrates ID-CDM's competitive diagnosis precision while ensuring the identifiability and explainability of diagnostic results. Figure 7 visualizes the learner traits diagnosed by different models, where ID-CDM's results exhibit a strong correlation with learners' actual performance, making it possible to distinguish between learners with different correct rates. This further demonstrates ID-CDM's explainability on response data from a statistical and visualization perspective. The authors conclude that ID-CDF effectively addresses the non-identifiability and explainability overfitting problems in CDBA-SED learner modeling, providing identifiable and explainable diagnostic results that can capture the complex interaction between learners and questions. The acknowledgments section of the research paper acknowledges partial support from various grants, including the National Key R&D Program of China, the National Natural Science Foundation of China, and the University Synergy Innovation Program of Anhui Province. The ID-CDM model, based on the encoder-decoder framework, offers a more accurate and explainable learner diagnosis compared to traditional cognitive diagnosis models. It addresses the limitations of existing models, such as the non-identifiability problem and explainability overfitting. The model consists of an encoder for semantic extraction from learner response logs and question response logs, and a decoder for predicting learner traits and question parameters. The computational complexity of ID-CDM is primarily determined by the number of learners, questions, knowledge concepts, hidden layers, and the dimension of each hidden layer. Experimental results on 3 datasets demonstrate that ID-CDM outperforms state-of-the-art CDMs in diagnostic and predictive accuracy, effectively identifying learner strengths and weaknesses. The authors conduct a comprehensive analysis of learner traits clustering using various cognitive diagnostic models, including the proposed ID-CDM, ID-CDM N-mono, CDM-FKC, NCDM, DINA, and MERT. The learner traits diagnosed by these models are visualized in Figures 10 and 11, where each point represents a learner's traits colored by their correct rate. The results show that ID-CDM and ID-CDM N-mono effectively identify learner traits that are linearly separable from correct rates, with the monotonicity condition in ID-CDM enhancing the correlation between learner traits and correct rates. In contrast, NCDM and CDM-FKC exhibit partial correlations between learner traits and correct rates, with learners being linearly separable in Math 1 and Math 2 datasets. The distribution of learner traits in ASSIST and algebra datasets is not linearly separable, with some points having negative labels mixed with others having positive labels. The diagnostic module of ID-CDM enables CDMs to learn the correlation between the shape of the distribution of learner traits and the distribution of correct rates, enhancing the discrimination ability of CDMs. The authors also examine the performance of DINA and MERT models, which exhibit limited correlation between learner traits and correct rates, except for DINA in Math 1 and Math 2 datasets. The dichotomity of learner traits in DINA limits its ability to capture the correlation between learner traits and response patterns, highlighting the importance of considering nuanced learner traits in personalized learner modeling. The comparative analysis of learner traits diagnosed by various models, including ID-CDM, DINA, MERT, U-auto-rec, and CDAE, reveals significant differences in their correlation with correct rates. The ID-CDM model stands out for its strong correlation and distinct clusters for each trait category, indicating the effectiveness of its diagnostic modules and monotonicity condition. In contrast, the DINA model shows a weaker correlation, the MERT model exhibits an irrelevant distribution, and the U-auto-rec and CDAE models display partial correlation with nonlinear distributions. This highlights the strengths of the ID-CDM model in diagnosing learner traits and their relationship with correct rates, emphasizing the importance of its design elements in enhancing diagnostic feasibility.